Okay, so some general definitions. So we've been talking about this in terms of velocity and position. So I'm going to break this off. I did not leave myself that much room to do this, so I'll try to squeeze this in there. So suppose we have a function defined for x between x1 and x2. So by that I mean that its domain at least contains the interval from x1 to x2, and it could be larger. Okay, then two things. The change in f over the interval x1 to x2 is just f of x2 minus f of x1, and the abbreviation that we use for this is delta f, right? And the x1 and x2 aren't contained in this notation, so it's sort of implicit that that is the interval that we're talking about. Okay, so this is change, and then the other definition I wanted to give you was the average rate of change. So this is very similar to the average velocity that we talked about earlier. Okay, just zoomed in all of a sudden. Okay, average rate of change. And I will usually abbreviate this AVG and then ROC. So average rate of change of the function f from x1 to x2. You could also say over the interval x1 to x2. This is just the change in output over change in input. Right. So in terms of this notation, that would be delta f over delta x, and then that is just f of x2 minus f of x1 over x2 minus x1. Okay, so we have change, we have average rate of change. We also talked about instantaneous rate of change, but we don't have a formula for that yet. Okay, one thing that you might notice is that this formula, it looks just like your formula for finding the slope of a line, right? So for finding the slope of a line, and it really is connected to finding the slope of a certain line. And remember that I told you that the slope is a rate of change, and that linear functions that have obviously a slope, they have constant rate of change. Okay, so let's talk about secant lines. These are the connection between average rate of change and the slope of a line. So computing the average rate of change of a function actually comes down to basically assuming that your function behaves like a line, okay? So what do I mean by that? So if you had, say, here was your x1 and here was your x2, and you were computing the average rate of change of your function over that interval. So let's see. It's right there, so what you would be computing when you found the average rate of change would be the slope of this line right here that I drew. And notice that it goes through the graph at the point x1 and also at x2, right? So this is what we call a secant line. And a secant line is just a line that intersects the graph of a function at two distinct points. Right? Okay, so here that would be at x1 and x2, how I've drawn it, and the slope of the secant line is, of course, so this is the point x2 f of x2, and this is the point x1 f of x1, right? And so it's just that same formula that I wrote down for average rate of change. Okay, so this is the connection between average rate of change and representing the average rate of change graphically. I'm going to get rid of this arrow here so it's a little cleaned up. Okay, so the slope of the secant line from x1 to x2 is the average rate of change of the function over the interval x1 to x2. I think, actually, I will write that down as well, just to make sure you have that. Slope of the secant line the average rate of change of the function right. Okay. Now in the same vein, we have something called a tangent line, and tangent lines correspond to the instantaneous rate of change, right? So we don't have a formula for this yet, but we know what the idea behind an instantaneous rate of change would be. So what is a tangent line? A tangent line, so it has to occur at a point, just like instantaneous rate of change. So a tangent line to a function at a point is just a line that touches the graph at that point and is sloped in the same direction. Of the graph. So you can see from this picture that this dotted line is a tangent line to this function at this point. We could call it A, right? And so one way of thinking about this is to think of a little car driving along your curve, right? And so imagine you have a little car like this, and the tangent line is showing where the headlights and the tail lights would be shining, right? So it will just follow this line, the headlights and taillights, right? So that's one way of visualizing this. So notice that each point you can get a tangent line. So here it would look something like that. At the bottom of this curve, it would be flat like that. And then here, so each of these. Okay, so that is the tangent line. I wanted to show you something that is on another screen. So let me see if I can do that. Oh, I think I have to drag it over. Okay. Okay, so I hope you can see this. So this is just a picture that's going to show, so my function here is this curved, this parabola, right, the red part, and then graphed on here I also have the purple line, which is the tangent line, and the green line is the secant line, which goes through the same point as the tangent line over here, and then it goes through a different point here. And what I wanted you to notice here is we can move, so we can move the secant line around, and if we take it closer and closer to that point where we have the tangent line, see that this green line, it gets closer to this purple line, right? So it's getting closer, the slopes are sort of converging to the same thing, and if we get really close, they're basically on top of each other like that, right? So this is the idea of a limit and how our secant lines are going to approximate the tangent line. And we will get into that later when we actually define the derivative. But I just wanted you to see, just to visualize the connection between the secant line and the tangent line, right? Okay.